I'm Bill Gropp, Director of the National Center for Supercomputing Applications at the University of Illinois and Vice Chair of SC20 Invited Talks. Welcome to the SC20 Invited Talk session on responsible application of HPC. The overarching theme of SC20 is more than HPC. Complementing this theme, the Invited Talks collectively focus on applications and technologies impacting all areas of science, engineering, medicine, and society. The distinguished speakers in this session share their insights into some of the applications domains that have a potential to significantly transform our daily lives. Lorena Barba is a professor of mechanical and aerospace engineering at the George Washington University in Washington, D.C. Her research interests include computational fluid dynamics, high-performance computing, computational biophysics, and animal flight. She is also an expert in research reproducibility and was a member of the National Academies Study Committee on Reproducibility and Replicability in Science. She was a recipient of the 2016 Lemur Rosenthal Award for Open Social Sciences under the Leaders in Education category.
Hello SC20 friends and colleagues. I'm Lorena Barba. It is a privilege to be an invited speaker at SC20, and I want to thank the Invited Talks Chair, Sadaf Alam, of the Swiss National Supercomputing Center, the co-chair, William Gropp, of the National Center for Supercomputing Applications and the University of Illinois in Urbana-Champaign, and the rest of the committee. Thanks very much. This session's theme is responsible application of HPC, complementing the SC20 overarching theme of more than HPC. And I was invited to speak about my work and insights on transparency and reproducibility in the context of HPC. The title of my talk is Trustworthy Computational Evidence Through Transparency and Reproducibility. I was the SC19 Reproducibility Chair, leading an expansion of the initiative at the time, which was placed under the technical program that year. We moved to make the artifact description appendix required for all SC papers. We created a template and an author kit to assist authors in preparation of their appendices, and we introduced 3 new tracks. The artifact description and evaluation appendices track with an innovative double open and constructive peer review process, the reproducibility challenge track, and the journal special issue track for managing the publication of select papers from the Student Cluster Competition Reproducibility Challenge. This year, the initiative was augmented to address issues of transparency, in addition to reproducibility, and a community sentiment study was launched to assess the impact of the effort 6 years in, to canvass the community's outlook on various aspects of it. I want to especially ask a few people. Here they are: Mike Haru, Reproducibility Chair for SC in 2017 and 2018, Michaela Taufer, the SC19 General Chair, who put her trust in me to inherit the role from Mike, and to Beth Plale, the SC20 Transparency and Reproducibility Chair. I had countless inspiring and supportive conversations with all of them, with Mike and Michaela during the many months of planning for SC19, and many more productive conversations with Beth during the transition to her leadership. Mike and Michaela and myself have served together in other committees and several other working groups, in particular, one that met in July of 2017, the workshop on reproducibility taxonomies for computing and computational sciences at NSF, convened by Almadina Chichalkanova. My presentation at that event condensed an inventory of uses of various terms like reproducibility and replicability across many fields of science. And then I wrote a review article on this topic, Terminologies for Reproducible Research, and posted it on arXiv. It informed our workshop's report, which came out a few months later as a Sandia report titled Toward a Compatible Reproducibility Taxonomy for Computational and Computing Sciences, in which we highlighted that the fields of computational and computing sciences provided 2 opposing definitions of the terms reproducible and replicable. The Association for Computing Machinery, ACM, representing computer science and industry professionals had recently established a reproducibility initiative and adopted diametrically opposed definitions to those used in computational sciences for more than 2 decades. In addition to raising awareness of the contradiction, we proposed a path to a compatible taxonomy in this report. Compatibility is really necessary here because computational sciences, that is astronomy, physics, epidemiology, biochemistry, all these fields that use computing intensely, and computer science tend to have shared venues where they present their work. SC, of course, is one of them. Given the historical precedence of the usage in computational sciences, our Sandia report recommended that the ACM definitions be reversed. Several ACM-affiliated conferences were already using the artifact review and badging system that was approved in 2016 by ACM, so really this was no modest suggestion. But the report did raise awareness and invited for discussion and thinking about this and addressing it further down the line. A direct outcome of the Sandia report was a proposal to the National Information Standards Organization, NISO, for a recommended practice for a badging scheme for reproducibility in the computational computing sciences. NISO is a non-profit organization accredited by ANSI, the American National Standards Institute, to develop, maintain, and publish consensus-based standards for information management. The organization has more than 70 members, including publishers, information aggregators, libraries, other content providers, which all use its standards. I co-chaired this particular working group with Jerry Grenier from IEEE and Wayne Graves from ACM. Mike Carew was also a member. The goal of the Reproducibility Badging and Definitions Working Group was to develop a recommended practice document, recently published and available after public discussion, public comments. This is a step before a standard, but as part of our joint work, we also prepared a letter for ACM Publications Board, which was delivered in July 2019. The letter gave some context and highlighted the incompatibilities in definitions and made a concrete request that ACM consider a change. By that time, not only did we have the Sandia report as a justification, but the National Academies of Science, Engineering, and Medicine had just released the report on reproducibility and replicability in science. This was the product of a long consensus study over 18 months with 15 experts, including myself, and sponsored by the National Academy, the National Science Foundation, under a congressional mandate. The National Academies report put forth its definitions as follows. Reproducibility is obtaining consistent results using the same input data, computational steps, methods, and code and conditions of analysis. Replicability is obtaining consistent results across studies aimed at answering the same scientific question, but each of which has obtained its own data, possibly with different methods. So the key contradiction with the ACM badging system resides on which term comprises using the author-created digital artifacts, whether it's replicability or reproducibility that uses the same data and code. We stated in the letter that if ACM were to consider reversing its definitions, then the working group would be able to move forward in its goal of drafting recommended practices for the field of information management, and this would probably lead to wider adoption in other technical societies and publishers. The ACM actually responded positively. They began working through the details on how to make changes to items already published in the digital library with the results replicated badge. Nearly 200 items already existed with this badge. Over the summer of 2020, the ACM applied some changes to the published artifact review and badging web pages and introduced a versioning number, as you can see here, version 1.0, We see already on this page a note added. You can barely read it at the bottom, but if you visit this webpage, you'll find a note indicating that the ACM had conversations with the NISO leading to this revision and the goal of harmonizing the terminologies. And indeed, they made a change. Version 1.1 has the reversal, and the term reproducibility at this point concerns using the author-created artifacts, whereas replicability is a more broader, more general term where a different group may create their own methods or collect their own data. All this background serves just to draw your attention to the prolonged, thoughtful, and sometimes arduous efforts that have been directed at charting paths for adoption and giving structure to reproducibility and replicability in our research communities. I was part of a panel illustrated in this photo from SC16 that already was discussing these issues. And so really this first part of the talk is to give you background, to give thanks and give credit, and to establish my credentials on the topic. But let me move on now to why and how might the HPC community move forward. Deployed just over a year ago, the NSF-funded Frontera system at the Texas Advanced Computing Center, TAC, came in as the 8th most powerful supercomputer in the world and the fastest on a university campus. Up to 80% of the available time on Frontera is allocated through the NSF Petascale Computing Resource Allocation Program. And the latest round of allocations for Frontera was just announced on October 25. So I read through the fact sheet of the 15 newly announced allocations to get a sense for the types of projects in the portfolio. 4 projects are in machine learning or AI-based projects, the same number as those in astronomy and astrophysics, and 1 more than those in weather or climate modeling. Other projects are single instances of spanning volcanology, mantle mechanics, molecular dynamics of ion channels, quantum physics and material science, and 1 single engineering project in fluid structure interactions. And so I could gather these HPC projects in 4 categories. First, the astronomy and astrophysics projects. This is a mature field that in general has a high community expectation of openness and reproducibility. But as I'll highlight a little later though, even these communities with mature practices benefit from checks of reproducibility that uncover areas of improvement. In a second category, the projects tackling weather and climate modeling are candidates for being considered of high consequence to society. One example from the Frontera allocations concerns the interaction of aerosols caused by industrial activity with clouds, which can end up composed of much smaller droplets. They become more reflective, and this results in a cooling effect in the climate. Now, global climate models tend to overestimate this radiative forcing, and this potentially underestimates global warming. So why? This is a question of really great consequence for science-informed policy in a subject that is already under elevated scrutiny from the public. Another project in this cluster deals with real-time high-resolution ensemble forecasts of high-impact weather events. So I submit that high standards of transparency, meticulous provenance capture, and investments of time and effort in reproducibility and quality assurance are justified in these types of projects. In another category, we have 4 winning projects that are applying techniques from machine learning to various areas of science. In one case, the researchers seek to bridge the gap in the trade-off between accuracy of prediction and model interpretability to make machine learning more applicable in clinical and public health settings. Now, this is clearly also an application of high consequence. But in addition, all of these projects face the particular transparency and provenance issues that affect all machine learning techniques. These require new approaches for transparent reporting and prospective provenance. In another category, we have the rest of the projects, which are classic HPC applications. These include material science, geophysics, and fluid mechanics. Now, reproducible research practices vary broadly in these fields and in various research groups, but I feel confident saying that all or nearly all of these efforts would benefit from prospective data management, better software engineering, and more automated workflows. And their communities will also grow stronger with more open sharing. The question I have is this: how could the merit review of these projects nudge researchers toward greater transparency and reproducibility? Maybe that's a question for later, and a question to start with is, how could support teams at cyber infrastructure facilities work with researchers to facilitate their adoption of better practices? I'll revisit these questions a little bit later. I also looked at the 2019 Blue Waters Annual Report that was released on September 15, 2020, with highlights from a multitude of research projects that benefited from computing allocations on the system. Blue Waters went into full service in 2013 and has provided over 35 billion core hour equivalents to researchers across the nation. And the highlighted research projects in this report fall into 7 disciplinary categories and include 32 projects in space science, 20 in geoscience, 45 in physics and engineering, and many, many more. I want to highlight just one of the many dozens of projects that was featured in this Blue Waters annual report. And for the following reason, I did a word search on the PDF with the word Zenodo. And that project was the only one listing Zenodo entries in the publication and datasets section that ends each feature. One other project did list, in the area of astrophysics, that other project did list or mention that data was available through the project website and in Zenodo, but it didn't list Zenodo entries in their references list. As many of you know, Zenodo is an open access repository funded by the European Union's Framework Programs for Research, and it's operated by CERN. And Zenodo, some of the world's top experts in running large-scale research data infrastructure are at CERN, where Zenodo is hosted. And so this is on top of infrastructure that is built in the service of what is the largest high-energy physics laboratory in the world. Zenodo hosts any kind of data under any license type, including closed access, and it has become one of the most used archives for open sharing of research objects, including software, especially with its GitHub integration. So the project I want to highlight is molten salt reactors and their fuel cycles, led by Professor Catherine Huff at UIUC. I've known Katie since 2014, and she and I share many perspectives on computational science, including a strong commitment to open source software. This project deals with modeling and simulation of nuclear reactors and fuel cycles, combining multiple physics and multiple scales with the goal of improving design of nuclear reactors in terms of performance and safety. As part of the research that was enabled by Blue Waters, the team developed 2 software packages, one called MoltRes, described as a first of its kind finite element code for simulating the transient neutronics and the thermal hydraulics in a liquid fueled molten salt reactor. And the other software called SaltProc, a Python tool for fuel salt reprocessing simulation. The references list in this feature include research articles in the Annals of Nuclear Energy, as well as the Zenodo deposits for both codes and publications about Moltres, one of the software packages in the Journal of Open Source Software, JOSS. And as one of the founding editors of JOSS, of course, I'm very pleased. Now, it's possible, of course, that other projects listed in the Blue Waters annual report do have software archives in Zenodo or have published in JOSS, but they did not mention or did not cite these items in their highlights. Now, clearly, the context of the project that I highlighted is of high consequence to society, nuclear reactor design. The practices of this research group show a high standard of transparency that should be the norm in this field. Beyond transparency, the publication of the software in JOSS ensures as well that it is subject to peer review. The software is subject to peer review, and that it satisfied standards of quality. JOSS reviewers do install the software, run the tests, comment on usability and documentation, and so it does lead to quality improvements. Next, I want to highlight the work of a group that includes SC volunteers, Michaela Taufer, and Eva Dielman. This was posted just last month on Archive. The work sought to directly reproduce the analysis that led to the 2016 discovery of gravitational waves, using the data and codes that the LIGO collaboration had made public and available to the wider scientific community. The data had previously been reanalyzed by independent teams using different codes, so leading to a replication of the results, but there had been no attempt yet to reproduce the original results. In this paper, the authors report on the challenges they faced during the reproduction effort, even if the availability of data and code supplementing the original publication was public. A first challenge was due to the lack of a single public repository with all the information needed to reproduce the results. The team had the cooperation of one of the original LIGO team members who had access to unpublished notes that ended up being necessary, the process of iteratively filling in the gaps to reproduce the work. Other highlights in the reproduction exercise include the original publication did not document the precise version of the software that they had used in the analysis. The script used to make the final figure was not released publicly, but one co-author gave access to it in the reproduction effort, so it was possible to do it. And the original documented workflow queried proprietary servers to access the data. And this reproduction needed to then modify that to run with the public data instead. In the end, the final result of this effort was that the result, that is, the statistical significance of the gravitational wave detection from a black hole merger, was reproduced, but not really independently from the original team, because one of the researchers is a co-author in both publications, and he was able to fill in the gaps. The message here is that even in a field where there's a mature, high standard of transparency and reproducibility, sometimes some checks are needed to ensure that these practices are sufficient or can be improved. And this brings me to my next section on science policy trends. The National Academies study on reproducibility and replicability in science was commissioned by the National Science Foundation under congressional mandate, with the charge coming from the chair of the Space, Science and Technology Committee. National Academies reports and convening activities have a range of impacts on policy and practice, and often guide the direction of federal programs. NSF is in the process of developing its agency response to the report, and we can certainly expect to hear more in the near future about requirements and guidance for researchers seeking funding. The recommendations of the National Academies report are directed at all the various stakeholders, including researchers, journals and conferences, professional societies, academic institutions and national laboratories, and funding agencies. Recommendation 6-9 in particular prompts funders to ask that grant applications discuss how they will assess and report uncertainties, and how the proposed work will address reproducibility and or replicability issues. It also recommends that funders incorporate reproducibility and replicability in the merit review criteria of grant proposals. Now, this combined with related trends urging for more transparency and public access to the fruits of government-funded research, I think we need to be aware of the shifting science policy environment. One more time, I have the reason to thank Mike Haru, who took time for a video call with me as I was preparing for this talk. In his position as a senior scientist at Sandia, 1/5 of his time is spent in service of the lab's activities. And this includes serving in the review committee of the internal laboratory directed research and development grants, LDRD grants. Now, as it is an internal program, the calls for proposals are not available publicly, but Mike tells me that they now contain specific language asking proposers to include statements on how the project will address transparency and reproducibility. These aspects are discussed in the proposal review, and they are a factor in the decision making. And as community expectations grow, it could happen that between two proposals equally ranked in the science portion, the tiebreak comes from one of them better addressing reproducibility. Already some of the projects and some of the teams at Sandia are performing at a high level. For example, they produce artifact description appendices for every publication that they submit, regardless of the conference or journal requirements. Now, we don't know if or when NSF might add similar stipulations to general grant proposal guidelines, asking researchers to describe transparency and reproducibility efforts in the project narrative. One place where we see the agency start responding to shifting expectations about open sharing of research objects is in the section on results from prior NSF funding. NSF currently requires here a listing of publications from prior awards and, quoting here, evidence of research products and their availability, including data and software. I want to thank, again, Beth Plale, who also took time to meet with me over video and also sent me some follow-up materials to use in preparing this talk. In March of this year, NSF issued a Dear Colleague letter on open science and research data, with Beth actually acting as the Public Access Program Director. Now, this DCL says that NSF is expanding its public access repository to accept metadata records, leading to data discovery and access. This requires the research data to be deposited in an archival service and assigned a DOI, a digital object identifier, a global and persistent link to the object on the web. A grant proposal's data management plan should state the anticipated archive to be used and include any associated cost in the budget. But notice this line at the end here. Data reporting will initially be voluntary, emphasis mine there. Now, this implies that it might later be mandatory. The DCL invited proposals aimed at growing community readiness to advance open science. And at the same time, the Office of Science and Technology Policy issued a request for information early this year asking, what could federal agencies do to make the results from research they fund publicly available? And well, by the way, the OSTP subcommittee on open science is very active. I want to highlight the MIT Library's public response to the OSTP request for information because it's quite interesting and comprehensive. I'm just picking up a few items from it. It recommends, among several other things, that policies that default to open sharing for data and code should be enacted with some opt-out exceptions available for special cases, privacy or security and so on, but it should be the default. That the agencies should consider providing incentives for sharing of data and code, including supporting credentialing or badging and peer review, and also encourage open licensing. And recognizing data and code as legitimate, citable products of research, and providing incentives and support for systems of data sharing and citation. The MIT Library's response addresses various other issues like responsible business models for open access journals and federal support for vital infrastructure that is needed to make open access to research results more efficient and widespread. It also recommends that federal agencies provide incentives for documenting and raising quality of data and code, and also, I quote, promote, support, and require effective data practices such as persistent identifiers for data and efficient means for creating auditable and machine-readable data management plans. To boot, the National Institutes of Health just announced in October 29 a new policy on data management and sharing. It requires researchers to plan prospectively for managing and sharing scientific data openly, saying, I quote, "We aim to shift the culture of research to make data sharing commonplace and unexceptional." This new policy takes effect on January 2023. Another setting where we could imagine expectations to discuss reproducibility and open research objects in proposals is allocations for computing time. For this section, I'd like to thank John West, the Director of Strategic Initiatives at the Texas Advanced Computing Center, who also took time for a video call with me while I was writing this talk. We bounced ideas about how cyber infrastructure providers might play a role in growing adoption of reproducibility practices. Currently, the NSF science proposal and the computing allocation proposal are awarded separately. The allocation submission guidelines discuss review criteria, which include intellectual merit, demonstrated by the NSF Science Award, methodology, including models, software, and analysis methods, research plan and resource request, and efficient use of computational resources. Now, for the most part, researchers have to show that their application scales to the size of the system they're requesting time on. But interestingly, the allocation award is not really tied to performance, and researchers are not asked to show that their codes are optimized, only that they scale and that the research question is feasible to be answered in the allocated time. Now, we all know that it's easier to scale slow code. The responsible stewardship of the supercomputing system is provided for via the close collaboration between the researchers and the members of the supercomputing facility. Codes are instrumented under the hood with low overhead collection of system-wide performance data, in the case of the UT facility, using what's called TAC stats and some web interface for reports. So I see three opportunities in this case. One, workflow management and or system monitoring could be extended to also supply automated provenance capture. Two, the expert staff at the facility could broaden their support to researchers to include advice and training in transparency and reproducibility. Three, cyber infrastructure facilities could expand their training initiatives to include essential skills for reproducible research. And John floated on few other ideas, like the possibility that some projects be offered a little bump in their allocations, say 5 or even 10%, to engage in reproducibility activities. Or maybe more drastic steps, like perhaps that projects may not be awarded allocations over a certain threshold unless they show commitment and a level of maturity in reproducibility. And this brings me to my final remarks. Next steps for HPC. The SC Transparency and Reproducibility Initiative is one of the innovative early efforts to gradually raise the expectations and educate a large community about how to address it and why it matters. Over 6 years, we have built community awareness and buy-in, and this year's community sentiment study shows frank progress. 90% of respondents are aware of the issues around reproducibility, and only 15% thought the concerns are exaggerated. Importantly, researchers report that they are consulting the artifact appendices of technical papers, signaling impact. As a community, we are better prepared to adapt to raising expectations from funders, publishers, and readers. Now, the pandemic crisis has unleashed a tide of actions to increase access and share results. The COVID-19 Open Research Dataset is an example. The COVID-19 Molecular Structure and Therapeutics Hub at MolSI is another. There are several others. Facing a global challenge, we as a society are strengthened by facilitated immediate access to data, code, and published results. This point has been made by many in recent months, but perhaps most eloquently in this community letter regarding sharing biomolecular simulation data for COVID-19. It was signed by more than 100 researchers from around the world, and I want to highlight Romy Amaro, who has been a vocal leader in open science in the past few months. The letter says, there is an urgent need to share our methods, models, and results openly and quickly to test findings, ensure reproducibility, test significance, eliminate dead ends, and accelerate discovery. Then it follows with several commitments. To make results available quickly via preprints, to make available input files, model building and analysis scripts, and data necessary to reproduce the results, to use open data sharing platforms to make available results as quickly as possible, to share algorithms and methods in order to accelerate reuse and innovation, to apply permissive open source licensing strategies. Funnily enough, these commitments are reminiscent of the pledges I made in my reproducibility PI manifesto 8 years ago. I've examined here in this talk several issues of incentives. And one thing the pandemic instantly provided was a strong incentive to participate in open science and attend to reproducibility. The question is, how much will newly adopted practices persist once the incentive of a world crisis is removed? Now, this issue of incentives comes up very often in our discussions. But social epistemologists of science know that so-called Mertonian norms, those that ask researchers to share results widely, those are supported both by economic and ethical factors, both by incentives and norms. These are in close interrelation. Social norms require a predominant normative expectation. For example, sharing of food in a social gathering under a given culture, that's a social norm. It might be widely expected. In the case of open sharing of research results, those expectations are not prime because researchers are sensitive to credit incentives. One philosopher has said it the following way: give sufficient credit for whatever you want to see shared, and scientists will indeed share it. In HPC settings, where we can hardly ever reproduce results because due to machine access, cost, and effort, a vigorous alignment with the goals of transparency and reproducibility will develop a blend of incentives and norms, will consider especially the applications of high consequence to society, will support researchers with infrastructure, both human and cyber, and over time, we will arrive at a level of maturity to achieve the goal of trustworthy computational evidence, not by actually exercising the open research objects, the artifacts that have been shared by the authors, data and code, that is, but by a research process that ensures unimpeachable provenance. With that, I am happy to conclude, and if this platform for SC20 allows, answer any questions. Thank you ever so much for listening to this talk, for engaging in this conversation, and I look forward to continuing the conversation in other media. Thank you.